What is going on, everyone, and welcome back to part 2 of my Everything You Need to Know About Capacitors series. Just a quick recap. In part 1, we learned about a capacitor as an ideal circuit element, and we kind of studied its behavior in various circumstances. So now what we're going to do is take a look at some real-life capacitors and learn about some of the practical considerations that you need to make whenever you're going to use one in some of your real-life applications and designs. So we're going to take a look at some data sheets, run a few simulations, and then go over some example designs to try to get an understanding of how capacitors are actually used in real life. But before we go any further, please go ahead and drop a like on the video for me. It helps my channel out a ton, and subscribe so you can stay up to date with any future videos. Okay, so just like in part 1, I want to first start off by going over the anatomy of the capacitor. But in this case, we're going to talk about the anatomy of the non-ideal or real-world capacitor. Because if you remember in part 1, I represented the capacitor as simply just two plates with some type of dielectric or insulator in between them. However, in real life, there are a lot of what you would refer to as parasitic elements that kind of affect the behavior of the capacitor. So let's just go over all of those parasitic elements right now. So starting off with this element up here, this is just a resistor, and this is known as equivalent series resistance, or ESR, of the capacitor. This element behaves exactly like a regular resistor. It dissipates energy in the form of heat and limits the current flowing into and out of the capacitor. So whenever it's charging and discharging, all of that current has to flow through this equivalent series resistance. The main things to look out for when it comes to ESR are how it impacts the thermal performance of the capacitor, because like I just mentioned, it's dissipating energy in the form of heat. So there will be a thermal consequence having an ESR value. And then also its frequency response characteristics. So we briefly went over some of the frequency response characteristics of a capacitor in part 1, and we'll dive more deeply into this later on in this video. Okay, so the next parasitic element I want to focus on is this inductor down here, which is known as equivalent series inductance, or ESL for short. So we haven't actually gone over the behavior of inductors on this channel yet, but understand that they are also a passive element whose behavior depends on the frequency of the signal being passed through them. So much like capacitors, they behave similarly in that way, but a little bit different. But the important thing you need to know is that inductors, or an ESL value, will affect the frequency response of our capacitor. So we'll see how that plays out later on in this video. And then lastly, this is a component we've already actually mentioned once before in part 1, but you have this parallel resistance known as R leakage. It's just a value that will constantly dissipate energy across the capacitor. The leakage resistance doesn't really have that much of an impact on the performance of a capacitor for most applications, but it's still important to understand that it's there. Okay, so now that we've gone over all of the parasitic elements in a real life capacitor, let's take a look at some of the key parameters that you should consider whenever you're evaluating a capacitor for your application. So I have here on DigiKey, I've went and pulled up just an example capacitor. This is an aluminum 100 microfarad, 450 volt radial cap, because we're going to take a look at a bunch of these parameters, and I'll just kind of break down what they mean and which ones are important. So the first parameter I want to draw your attention to, or I guess the first two I should say, is the ripple current limit. As we learned in part 1, a capacitor will try to supply infinite amounts of current in order to maintain a constant voltage. However, because of parasitic elements, there's actually a limit to the amount of current a capacitor can supply before it starts to overheat and damage itself. And that is what the ripple current value is. In terms of RMS, this is the amount of current that can flow into or out of the capacitor. So I want to show this example simulation. Okay, so what we have here is a simulation of a full wave bridge rectifier being filtered by a 102 microfarad capacitor across a 430 ohm load. So the first thing I want you to pay attention to is just watch the flow of electrons. As you see, we are charging the capacitor right now as current flows into the capacitor, and then now the capacitor is discharging as electrons are flowing out of the capacitor. What I have being plotted down here in this oscilloscope is going to be a graph of the current over time. So first thing I want you to notice is how it is, but sometimes it's positive and sometimes it's negative. Now, in terms of time, it's negative far more often than it is positive. As you see, if it drops below this x-axis, we're starting to get negative values. But then every now and again, it'll spike up positive very sharply while the capacitor gets charged. And then when it starts discharging again, we slope down back into the negative region. And so what ripple current is, it would be the RMS value of this graph over a particular region. So how do we calculate the ripple current value, you may be wondering? Well, one way is to run through a series of lengthy calculations in order to figure out what the value ends up being. So it would be this IC bulk RMS value, which we would have to back calculate this value, and then we'd have to back calculate this one. So it's a rather arduous process, I would say, to like do it by hand. You would have to follow a lot of steps in order just to calculate the RMS value. What I would instead propose is that we just simulate the circuit and then use the simulation to plot and calculate the RMS value of our graph over time, kind of like what we're doing now. But we need to use something a little more powerful than this simple circuit simulation tool I have that's on the internet. Instead, we're going to go to LT Spice in order to simulate the same exact circuit and measure its RMS value. So here we have another example of a full wave rectifier being filtered by a 100 microfarad capacitor in LT Spice. So we're going to run the simulation, and then we're going to measure the current that is flowing through the capacitor just like we did in the first simulation. So what we'll quickly do is we'll zoom in on a section until we can start to get a little more granularity and kind of see that we're kind of have the same shape curve, right, that we saw in the first example. Is it goes down below 0 to the negative, and then it pops back up, right? So in order to calculate the RMS value, what you'd ideally want to do, since this is a periodic signal, is just calculate the RMS value over one period. So we would go from like here, and then we could go to like, so from here to like here, I think would be a good way to start approximating, right? So by holding control and left clicking on the signal, I'm able to see that the RMS value for this capacitor is 1.8691 amps. And when I say RMS value, I mean that's the amount of current flowing into and out of the capacitor in RMS. So if I were looking for a capacitor, then I would need to make sure that its RMS ripple current rating is greater than this value in order for it to not like heat up, right? Another thing I want to go back and point out, so going back to this example, if you see there are two ripple current ratings, one is at low frequency and the other is at high frequency. So they give you the frequency rating here as well. So for low frequency, they say has 740 milliamp ripple current rating, and that's at 120 hertz. Looking at our example, this was actually using a 170 volt 60 hertz sine wave. So something you would see like a typical American 120 volt outlet has this peak value and this frequency. So this would be considered a low frequency application. It's close to 120 hertz for an approximation. So this capacitor right here would not actually work in this scenario because this ripple current rating is much too low. So we have to find one that has a much higher ripple current rating in order to handle it. Now, I also want to point out, though, is that the peak current of this thing is like 5 amps, right? So this would be an insanely high rated like power supply or something like that. So this is not a common application, right? I should have like increased this resistance to something much higher, like 500 ohms or something, to give you a more realistic expectation. But usually the load from this capacitor, usually the RMS current value is much lower, but there's something I know I just wanted to make. But everything we did in terms of like how we went about solving this problem is sound. Like you would simulate the circuit, then you would just control left click up here, and then it would tell you its RMS value. Alrighty, so I think understanding these two low frequency and high frequency conditions is a good segue into the next parameter that we want to kind of talk about, which is frequency response of your capacitor. As we learned in part 1, one of the most common applications of a capacitor is to act as a filter, specifically for high frequency noise that could affect the performance of a sensitive integrated circuit. In this instance, a capacitor's ability to filter out high frequency noise is very important. So understanding its frequency response curve is also very important. So I have here a 0.1 microfarad ceramic capacitor just as an example because these are very commonly used for filtering out high frequency noise. But I just want to pull up, I have one of the data sheets that comes with a capacitor. And so right here in the data graphs section, we see the frequency characteristics of the capacitor. And so what we have here on the x-axis is the frequency in megahertz, and we have the impedance in ohms. So like we talked about in part one, the relationship between the impedance of a capacitor and the frequency of the signal is inversely related. So just like this graph shows, as the frequency increases, the impedance decreases. However, if you see as we go higher and higher, eventually this actually reaches a local minimum, and then it starts to head the other way where its impedance starts to increase as we get up in the higher frequency ranges. And you're probably wondering, like, well, why is that? That doesn't make any sense why it's doing that. The answer to this question lies in the parasitic elements, specifically the equivalent series inductance that we showed earlier on, because inductor's impedance actually is directly proportional to the frequency of the signal, right? So as the signal frequency increases, the impedance of the inductor increases as well. So because of the parasitic inductance that is in series with our capacitor, that's why we're going to see the curve start to increase as it kind of overcomes, or as it sort of takes over the impedance curve, if that makes any sense. I should also note that ESR plays a small role, but it's not too significant in the grand scheme of things in terms of frequency response. So this is just something I wanted to point out, to know that it's not, a straight line down on forever. There is actually a point in which it changes directions. Okay, so now the next few are actually much easier, and so we should be able to get through them rather quickly. So the next one I want to focus on is the capacitor's voltage rating. A capacitor's voltage rating is pretty self-explanatory. This represents the maximum voltage you can apply across both pins before you actually start to cause damage to the capacitor. In most applications, it's extremely easy to find an appropriately rated capacitor even with some like additional headroom as well. You'll see a lot of these come in like 25 volt rating, 50 volt rating, 100 volt rating. Those are all pretty easy standard values that you can find for almost any value of capacitance. So, okay. And then the next one I want to talk about is the package or case that they come in. So with surface mount technology, you'll have a lot of those familiar package sizes. For example, this one is an 0402, but you'll also have things like 0603, 1206, very standard stuff that like you would see in the resistor section as well. There is a specific category of capacitor we'll talk about in a minute, known as the aluminum polymer category, but that one has surface mount package sizes which are a little bit irregular. And we'll dive into those in a little bit. They're not your like standard 06, 03, 04, 02. Just the whole shape of the capacitor is different. It's not really a chip. It's just like a radial can that's surface mounted pointing up. It's just also something to be aware of whenever you're picking a capacitor, is just understand what its package size is and how that can fit into the rest of your design from a layout perspective. And then there's also a through hole category of capacitors. So this first one, this is the first example that we brought up. So this is a radial can through hole. So it shows you the two important things to pay attention to are like the lead spacing. So it's the space between the two pins, and then like the size and dimensions. So it tells you the diameter of the can, and then it'll also tell you the height of the can. So that's kind of how the package is laid out whenever it's a radial can through hole capacitor. Selecting the right package size depends on the application. For example, with this ceramic capacitor, the surface mount, I usually like to start out with 0603 because that's sort of the happy middle ground between it's small and you can, you have versatility in terms of component placement. It can fit in a lot of places, but it's not too small to where you can't route between the pads, because that comes in handy a lot of times if you need to do that. But then sometimes, depending on the application, say I need to have like a really high density, spot on the board, I might go 0402, or if I'm trying to place them next to a microcontroller pin, which needs to have the capacitor really close by, I'll go with an 0402. But then also I might go with a 1206 if I'm assembling the entire board by hand, because those are a lot easier to handle than like 0603s. And yeah, that pretty much covers all of the main important key parameters that you should consider when selecting a capacitor. Now we're going to take a look at like the we're going to take a step back and kind of look at a broad overview of like the capacitor marketplace, kind of like what capacitors are available to be used in your designs, what are component suppliers and manufacturers making and selling right now, and like what are all the benefits, pros and cons of each different common type of capacitor. So I have here just the general capacitor section of the DigiKey website. So this is before we dive into any specific type of capacitor. So what I want to do is use this to give you a brief overview of all the options you have, and then we're going to dive into some of the most common types of capacitors. So just by like a quick glance, you kind of see how many items are offered in each category. So the largest item by far is ceramic capacitors at 700,000 items, right? So these ceramic capacitors are probably one of the most common types of capacitors you'll ever see in all of electrical engineering. Then following up that, you'll see aluminum electrolytic capacitors, which I would again say are probably the second most common type of capacitor you'll see in electrical engineering. Then after that, a lot of tantalum capacitors, which I will say are not as common as they used to be, and we'll talk about why that's the case in a minute. And then finally, we have aluminum polymer capacitors, which I would say are becoming more common, and we'll kind of talk about the applications that I've used them in a lot. So those are like the four main areas that I want to focus on when we're talking about real specific capacitors and kind of what they do, what their differences are. So let's just start with the largest category, which is ceramic capacitors. As I mentioned earlier, these are by far the most common category of capacitor, and their most common application is to like filter out high frequency noise around some type of integrated circuit chip. So you'll see them, they're really cheap. So you'll see them just all around the board. Anywhere where you think you might need to be, worried about high frequency noise, you'll see a filtering cap on there. These would be on anything from like a signal trace from an op amp to some type of, buck regulator line in order to make sure it has a clean signal being fed into the power pins of some type of integrated circuit. They have super low equivalent series resistance. They come in really small package sizes, and then they have a desirable frequency response curve across the entire, and they have a desirable frequency response curve across a broad spectrum. When being used as a sort of noise filter, or aka a bypass capacitor, these capacitors aren't supplying large amounts of current to a load, so they don't really need to have a high ripple current rating. In addition to that, since they also have really low ESRs, their thermal performance is not really of concern either. So one good example of a ceramic capacitor in action is on the output of a buck regulator as like a noise filter, right? So let's just zoom in right here. You see we have a 0.1 and a 0.01 microfarad capacitor. These are both ceramic capacitors, and they're acting as high frequency noise filters on the output of this buck regulator. We're using a different kind of capacitor to really smooth and supply lots of the load current, because you see this is a 5 amp load. So we're not counting on this 0.1 and the 0.01 microfarad capacitors to supply that 5 amp load current. We're using them just to try to help clean up the signal, because this is going to be supplying current to perhaps some other ICs or anything where we want just to have a clean signal in general. Another point I want to touch on is the reason we're using this array of capacitors or more than one ceramic capacitor is because going back, it's that frequency response curve that we just showed. Let me see if I can pull it up real quick. It's this frequency response curve right here, because by using different value capacitors, we actually can take advantage of combining their frequency response curves. Let me do a quick demo in an LT Spice simulation for you to show you what I'm talking about. So I have here an array of capacitors, and I just want to show their frequency responses individually. So this first one is an ideal capacitor, C4. Is an ideal capacitor. So whenever I plot its frequency response curve, you see a straight line. There's no equivalent series resistance. There's no equivalent series inductance to worry about. So we just get a perfect clean straight line. But then C1 shows this is an imperfect curve, right? You see we have that local minimum, and then it starts to rise again. Let's get rid of this, right? So see how it differs from an ideal capacitor, okay? And then so C2 is the same story. It's a non-ideal capacitor, but it has different ESL and ESR values, so it changes its total frequency response curve. And then C3 is the same story, right? So has different ESL, ESR values, different capacitance, so its frequency response curve is different. So if we look at this frequency response curve, we can see that each capacitor provides a super low impedance pathway to ground only during certain portions of the graph, right? So in this area, it's the light blue region, but then the light blue region is higher than the red region here. So then the red region is doing more work. And then here, the dark blue region is the lowest out of all three, right? So it's doing more of the work as you move up the frequency spectrum. So we're trying to take advantage of each capacitor's strong suits, strong areas of the curve, and using them together in unison enables us to have a superior frequency response curve than we could if we used just one single capacitor, if that makes any sense. Alrighty. Okay, so the next one I want to talk about is the aluminum electrolytic capacitors. So we kind of already touched on the primary use case for an aluminum electrolytic capacitor. The most common use case for an aluminum electrolytic capacitor is to filter out low frequency signals that require large amounts of current. So when we first look at this capacitor, we saw that it has a pretty good ripple current rating at low frequencies, right? At like 100 hertz, we have a pretty good ripple current rating. The most common use case for an aluminum electrolytic capacitor is for filtering out a low frequency, high voltage, relatively high current signal. For example, on the output of a full wave bridge rectifier like we showed in one of the previous examples. Aluminum electrolytic capacitors have great ripple current ratings at lower frequencies. They come in really high voltage ratings, so this one's like 450 volts. And you can also get really high capacitance ratings for relatively cheap, so that makes them an ideal source for power supplies. So here showing another example of them actually being used, we have a flyback converter circuit. We have a flyback converter, and here on the output of the bridge rectifier, we have two aluminum electrolytic capacitors. So one little pro tip, if your load current is extremely high, putting multiple capacitors in parallel will help really drive down the amount of ripple current that each capacitor observes, which if you understand Kirchhoff's current law, you would understand that the amount of current required by each individual capacitor is greatly reduced whenever you add multiple capacitors in parallel. So this is just a great example of an aluminum electrolytic capacitor being used. Alrighty, so the next one I want to talk about, so here's just an example of an aluminum polymer capacitor. And what aluminum polymer capacitors are great at is filtering out high current, high frequency, low voltage signals, for example, on the output of a buck regulator. So we'll take a look at this circuit again, and you see here, this 33 microfarad capacitor is an aluminum polymer capacitor. And so the characteristics of these are you can find them in pretty high capacitance values fairly easily, but they have limitations with their like rated voltage, right? It's kind of hard to find them up there in the range that you might find an aluminum electrolytic cap, but they have insane frequency, ripple currents at high frequencies. So that makes them really good for like a buck regulator typically operates at like 100 kilohertz all the way up to 1 megahertz. So that's why these are ideal for buck regulators. And one thing I forgot to mention about the aluminum polymer and the aluminum electrolytic capacitors is they're called polarized capacitors, meaning they have a positive pin and a negative pin. That's why there's a little plus right here on the symbol, because if you wire these in reverse, like you could wire this ceramic capacitor either way, right? You could flip this around and it would still work fine. If you did that with the aluminum polymer capacitor, it would blow up, right? Because they use electrolytes as their dielectrics, as that insulative, material between the plates. So wiring them backwards would reverse the chemical reaction and it would actually just cause it to blow up. Alrighty, so the last one on our list is the tantalum capacitor. So the tantalum capacitor is also a polarized capacitor, meaning it has a positive and a negative pin. So you have to make sure you wire it correctly as well, or else it will blow up. So describing the use case of a tantalum capacitor is kind of difficult because advances in modern electronics have rendered them a lot less useful than they used to be. One of the advantages of a tantalum capacitor used to be that you can get high capacitances and low package sizes, means that a lot of really high capacitance density, specifically in like the 1 microfarad to 10 microfarad region. It was pretty hard to find a ceramic capacitor that could give you that. And tantalum is where those were frequently used. Tantalum capacitors offer a good frequency response across a broad spectrum, much like ceramic capacitors do. That's one area where they would be used as high frequency filters, and they're also very stable across a broad frequency spectrum as well. So I don't actually really use tantalum capacitors in a lot of my designs, but one example where I could see one being used is say like on this example right here, I have a 5 volt 300 milliamp buck regulator. So this is a pretty low current draw, so we don't need something like an aluminum polymer capacitor because our ripple current rating is going to be very low. But say we need something really, really stable, like we need a really high amount of capacitance for this because we want to be extra clean, extra stable because it's going to be going to something very sensitive. I might use a tantalum capacitor to do this because I can get a really high capacitance value in a small package size, and then that would help me out. As I mentioned before, A ceramic capacitor could also do this job. In fact, I'm pretty sure that's what I did use here is a 22 microfarad ceramic capacitor. But this is just an example of a case where I could see it being used. And with that, pretty much wraps up everything I wanted to cover in part 2 of this video. Hopefully with part 1 and part 2, you're now like ready to go on and start using capacitors in your own designs. I went over some of the most common examples of capacitors being used and all the different kinds of capacitors you kind of have at your disposal. So yeah, if you have any questions about this, just go ahead and drop a comment down below. I respond to every comment I get, and I'll be happy to explain it or make another video. Thank you so much if you made it to the end of this video, and hopefully I will see you in the next one.